In this video, we will discover how computers stretch, rotate, and even translate 2D images using linear and affine transformations. Then we will animate a spring mass system in Python using transformation matrices. My name is Logan, and I hope you learned something new. Let's start by drawing a spring. Let's call the top of the spring the origin, and give the spring a length of 1. Using the grid, we can write down the coordinates of each dot. By representing an image as a collection of points, we can manipulate the image just by playing with the points. For example, we can stretch the spring by multiplying the y-coordinates by a constant. Stretching is a type of linear transformation. We represent a linear transformation with its transformation matrix T. We left multiply the xy vectors by t to compute the new coordinates for the spring. So why does this work? When we left multiply xy by t, we get xay. The y-coordinates have simply been multiplied by a constant, which corresponds to stretching the spring. In addition to stretching, we can use transformation matrices to scale, shear, reflect, or even rotate our image. We can combine transformations by multiplying the transformation matrices together from right to left. For example, we can shear and reflect an image in one operation. One thing that a 2x2 transformation matrix cannot do is translation. If we want to move an image across the screen, we need to use something called a 2D affine transformation. When we multiply, we see that the x and y entries have been shifted by a and b. In order to perform matrix multiplication, we had to extend the xy vector to include an additional entry. By convention, the additional entry is a 1. If we look at the anatomy of the affine transformation matrix, we see that the top left 2x2 block is just a transformation matrix. This allows us to perform a linear transformation and a translation at the same time. For example, we can shear and translate an image with the following matrix. The last row of the affine transformation matrix is always a bunch of zeros followed by a 1. The last column contains the shift amounts a and b followed by a 1. Because affine transformations can still perform the function of linear transformations, most software uses affine transformations for every single linear transformation or translation, including Matplotlib. In fact, every animation shown in this video so far has used an affine transformation. Now let's see how we can use affine transformations to animate a spring mass system. First, we will write down the ODE describing the equations of motion of the system. Then, we will create a function to generate points on the spring. This is exactly what we did at the beginning of the video. In our animation function, we use the Affine 2D from Matplotlib's Transformations module to obtain our matrix, which stretches the spring proportional to the height of the mass for each frame. We simply left multiply the original spring position by the affine transformation matrix to obtain the new coordinates of the spring. Here's the animation of the pendulum along with a time domain plot and a phase diagram. The code for this animation is provided on GitHub, link in description. In the next video, we will simulate a spring pendulum in Python. If you learned something new, please leave a comment below, and as always, please like and subscribe to encourage me to make more videos. Thank you!